engine and rocket. Ducted combination, ducted jet engine means air breathing plus non-air breathing. So for example, you have a hypersonic missiles. So it travels first using a ducted jet engine, which is air breathing engine, and then they switch off the air breathing engine, turn on the rocket engine to move faster lah. All right. So chemical, you have liquid, solid, and hybrid. Liquid rocket, both oxidizer and fuels are in liquid state, while solid propellants, both the fuel and oxidizer are in solid, and it is blended. It is like a fireworks lah. But hybrid, this is what I am working on. Hybrid, it is where the solid and where it is where the fuel and oxidizer in different physical state. The fuel in solid, the oxidizer in liquid. Okay, and then you have nuclear rocket engine. Nuclear rocket engine, currently it is not used during the launch, okay, launching or takeoff or ascending. It using during the cruise condition, okay, during the cruise. Electric rocket, similar. Electric rocket, they do have three types: electrothermal, electrostatic, and magnetoplasma. Okay, again, electric rocket does not being used during the takeoff, during the launching lah. It used when during cruise. Why I am saying this? Because this electric rocket, thrust that it produce, it is 1 Newton and below. It's very low. Okay, so that is why it is normally used during the altitude, the satellite, the trajectory, and etc. Because the satellites, it's already moving. Only a few millinewton it can move away lah. It has its own, yeah. And then the last one is other propulsion rocket concepts such as solar thermal and solar sails. Okay, I will show you the picture. All right, so these are the common launch vehicles. Chemical rockets, you know this. Nuclear rocket, it is up there, but it's still it's not fully utilized, the nuclear rocket lah, because it is dangerous, radioactive lah. Okay, electric rocket, as you can see top right. Okay, this is like a Iron Man. And then the combined ducted rocket, this is where combined between air breathing engine and non-air breathing engine. This is non-conventional. Yes, I know it is a little bit of scientific science fiction, but it is feasible mathematically and physically. But engineering, not yet. Solar sail, yes. Okay, maybe the students can ask. Solar, how come you can sail in the outer space? You don't have any wind, or maybe you don't have any air outside the system. But outside the system, we do have light. So light is what carries photons. So these photons bombard the sail of the solar panel. All right, and then gas tube hypersonic launcher, currently they have this. If you can try to Google the spin launch company in the United States, they have proven the prototype up to 100 kilometer to shoot the, what do you call it, a capsule to 100 kilometer using a launcher, spin launch. Okay, so actually what are rockets? So the simple to know what is a rocket all about, it is you want to convert the chemical energy to energy during combustion, and then into kinetic energy. So all of you know in physics, we do have conservation of energy. Yeah. So chemical energy burn. So that's why you have high temperature. You burn inside the thrust chamber here. So thrust chamber here. This is the what do you call it? The station P1, A1, and P1. Pressure 1, area 1, temperature 1. So you will burn. You take the chemical energy. You burn. So you will get heat energy. So this huge energy at high P, high T, it is then converted into kinetic energy. The gas is expanded out. The gas is expanded and accelerated out. So that's why you have accelerated through convergent and divergent nozzle. So convergent means that the area shrink. Divergent, it is where the area expand. So why does in rocket we do have convergent and divergent nozzle? Because we are dealing at extreme condition. We are dealing with compressible flow. Compressible flow, it is density reduced. So it is vice versa. It is vice versa as compared to incompressible flow. In incompressible flow, as you shrink area, velocity increases. But in a compressible flow, you increase the area, you will get high velocity. So when you have high velocity expel out from the exit of the nozzle, so you will get thrust lah, action and reaction. So the working principle is the thrust by the it produce thrust by ejecting matter, which we call as the fluid propellant outside, and which is then where the fuel is stored in the entirely of the flying vehicle. So that is the idea. No matter what do you call it, what are types of the rockets, electric rockets, nuclear rockets. This is the basic principle. You want to inject out as much as big enough of the propellant, or as fast enough of propellant. Okay, big and fast. All right, why I'm saying this, later we will look at the equation. So in a rocket science, are all the same? No. Okay, but usually happen, SpaceX launch their Starship, this morning. All right, so you can see that usually SpaceX, who else? Blue Origin uses chemical rocket. Uses chemical rocket in the form of liquid lah. Okay, but ESA, European, like Ariane, okay, Ariane 5 or Ariane 6, they usually use solid and liquid rockets. All right, and then the rockets, electric rocket, non-conventional rockets. So not all rockets are the same. So why does rocket is needed? Of course, because they have their own mission to send something, to send payload, to send a capsule, to send man into the ISS, into the moon, as well as sending medicine, food to the International Space Station lah. Okay, and then it comes from the trajectory, its own trajectory. So we do, although the trajectory is highly mathematical, but computer help us to calculate the trajectory, using that some of the rocket equation, Davorsky equation. All right, and also rocket also needed for orbit change and maneuvers. So like I said just before, that we use electric propulsion, electric rocket for the altitude control, to adjust, okay, to adjust the satellite to move. Okay, for example, let's take a James Webb telescope. Okay, James Webb telescope is a space telescope, putting at the L2 orbit. So me as a scientist on Earth, I write a proposal to the operator, James Webb operator, so that I want to study at the corner of this sky, okay, at this space. So when I write a proposal, and then of course they will decide if my proposal is approved, so they will adjust the Space Webb telescope to that particular spot that I have intended to look at. So this is what we call as attitude control lah. All right. How do rocket works? Of course, you will see later throughout this semester. We are talking about thrust. We are talking about specific impulse, weight flow rate, and staging. What is staging, brothers and sisters? Staging is it is where the rocket separate from one another. So this is what we call as multi-staging. So why do we need multi-staging? Is because we want to save weight. You can have one only, but this what do you call it? This mission is not well planned, not good. The rocket when it is finished, better to let it go. Okay, let it down, or maybe reuse like what SpaceX has done. All right, and the rocket also, when it is launched, it does not go vertically straight upward. It goes fly upward, but later it needs to turn. So this is what we call as a gravitational turning. Why we need gravitational turning? Because we want to save fuel. If you go straight upward, you will need more fuel to to combat with the gravity pull lah. Okay. How do rocket engine works? Of course, we cannot run away from thermodynamics and nozzle theory. Why nozzle theory? If you can see the nozzle itself, it is very impressive device. You are only play with the area you can gain so much thrust. So that is why I really I really what do you call it see nozzle as is a good invention lah. Okay, you play with the area, then you will get more thrust. Okay, but so maybe we can just expand as big as you want now. No, it's not like that. Why I am saying this? If you put the what do you call it angle bigger, there will be a separation occur inside the nozzle. Means that the gas, the propellant, does not expand entirely. Okay, you will see later separation occur inside the nozzle lah. Okay, rocket engine area ratio. This is for solid rocket, where the propellant inside, the solid propellant, the hole inside, as compared to the throat of the nozzle. So you have this what you call a ratio of 4. If you are going more than 4, you are fine. But if the ratio is less than 4, you will gain trouble where the pressure will rise up, or maybe you lose some thrust lah. Okay. So some of mathematical formulation, I took this from the website. So of course, you know already, you have lift, you have weight, you have drag thrust, and using the Newton's law, second Newton's of law, where the F equal to ma. So from this F equal to ma, the top one, okay, the top one in the middle, from this, they derive the equation include the pressure imbalance between outside and inside. So you have this equation. So for rocket, this is the mother of the equation. F is equal to m VE plus difference in pressure multiplied by A. So pressure multiplied by A is force lah. So P is equal to F over A, isn't it? So this is imbalance pressure. So F is thrust, m dot is the propellant mass, kilogram per second, mass flow rate. VE is the exit velocity plus the imbalance pressure. So you have imbalance pressure, and then you have momentum thrust. This is momentum thrust, this is imbalance pressure. So looking at this equation, okay, let's talk about the optimal, okay, the optimal condition, or we call this as a design condition. PE, what we want when we want to design a rocket, PE is equal okay, PE is equal to P ambient. PE is P exit, P naught is ambient lah. So when it is equal, this imbalance pressure is equal to 0. So what is left? M dot multiplied by the VE. So what I say just now, remember, it is to get the thrust, forward thrust, it is either you exit the propellant as big as you want, which is m dot, big m dot mass flux, or you injected the propellant at high speed, velocity exit. So this is an idea. Okay. So, but in electric rocket, electric rocket, VE is so fast. So in electric, very high speed. But what are they injecting? Ion. Ion is not that big. We are talking about the ion, which is the mass. The ion is very small. So multiplied by the VE. So that's why the thrust is not larger than 1 Newton. Okay. So this is the equation, rocket equation lah. Okay. So next, in a rocket, of course, it is solid motor. This solid motor, we will see later in a solid propellant chapter. We have erosion, burning, and etc. So during the burning for solid rocket, it will shoot rise up, and then it what we call as regression thrust. Okay, regression thrust means that it is reducing until a certain time. Okay, the most important part in a rocket design is, of course, the nozzle. Nozzle is a very impressive design of device. So using this configuration, convergent and divergent nozzle, we do have the mass flow rate equation. I will again, if not me, maybe Dr. Hugh will share you about the mass flow rate inside the nozzle. So A star is the area speed, T is pressure at throat, temperature at throat, gamma specific heat ratio, R gas pressure, and then this is the relation to find the m dot. Exit Mach number, AE, exit Mach number, and A star. A star, it is at the throat. A star is at the throat where the velocity Mach number is equal to 1. Sonic speed. Okay, so this is the equation. How they got this equation? Because using the momentum balance, energy equations. Okay, and then that's why I got this. And ME is exit Mach number. Exit Mach number. All right. Exit temperature, this is how they calculate again, brothers and sisters. These are all zero dimension. Not zero, I think one dimension. Yeah, one dimension, because it is from left, the thrust chamber, the throat, and then the exit condition. Okay, one dimension, sorry. All right. Velocity exit, exit pressure, and then VE. So this is isentropic relation, using isentropic relation. I know this is a very simple one, but they do have many assumptions. One, we have to assume that it is an isentropic. What is isentropic? Isentropic means that the entropy S1 and equal to S2 lah. Okay, isentropic, the entropy does not change, and it is adiabatic. When it is isentropic, it is adiabatic lah. Okay, adiabatic, no heat transfer to the surrounding. All right, and then this is conservation of mass. Of course, you know this. M dot is equal to rho AV, rho density is velocity. Don't confuse. My student always got confused between this V and the other V. Where's the V? Not here. Okay. So here rho VA. So V is not volume. V here is velocity. Yeah. Why you student get too confused? Because we have many V, and this V, how do you know that this V is velocity? Because we have m dot. M dot is kilogram per second. So you do have a function of time. Density, you don't have time. Volume, you don't have time. Area, you don't have time. So that is why V here is velocity. So this is the equation for isentropic momentum and thrust. Okay, look at this. This is what I told you. Why does a rocket nozzle must have converged and diverging nozzle in a subsonic flow? In some increased area, will increase in area, the velocity reduce. But supersonic flow, increase area, velocity is increased. All right. So this is what I mentioned before. So let's watch this video. Let me share this
Imagine
video.
this.
This is the
Let's say you want to
Chomsky
set up a
equation.
small satellite of some kind in low Earth orbit. Since we're in the 21st century, chances are that your selected mode of transport would be via rocket. Unfortunately,
Oh,
NASA does not want to support your endeavor. Taking matters into your own hands, you decide to make the rocket yourself. So, how do you make a rocket? Of course, you need a rocket engine, perhaps a compartment to put your payload in, maybe some tanks to store your propellant. Hey, speaking of which, how much propellant do you need? In the year 1903, Russian scientist Konstantin Tsiolkovsky derived an equation that can answer this very question. The equation looks something like this. This equation is called the Tsiolkovsky rocket equation. It can also be called as a classical rocket equation, the ideal rocket equation, or sometimes just the rocket equation. Yeah, but what the heck does it mean? Well, okay, then let's figure out what each variable stands for. On this side of the equation is delta V. It tells us the change in velocity the rocket can make. On the other side, we have exhaust velocity, which is how fast the propellant is expelled backwards relative to the rocket. M sub I, standing for initial mass, is the total mass of the rocket before firing the engine. M sub F, standing for final mass, is the total mass of the rocket after firing the engine. From a glance, what can this equation tell us? What does it imply? For one, it tells us that it actually doesn't matter how much propellant we bring. What matters is the proportion between the propellant mass and the total mass of the rocket. Yeah, that's cool, but where did the equation come from? Valid question, but a warning, it may get a little mathematical. According to Newton's second law of motion, we know that the sum of the forces acting on an object is equal to the mass of the object times its acceleration. Let's move the mass to the other side. We also know that acceleration is the derivative, or rate of change, of velocity. Therefore, velocity is also the antiderivative of acceleration. With a little substitution, we should get this equation. The force on a rocket is equal to the thrust of the engine, which is equal to the exhaust velocity multiplied by the mass flow rate, which is how much propellant is ejected per second. We know that the mass of a rocket constantly changes because it's constantly ejecting propellant. We can write mass as a quantity that changes with time, defined with this function. Of course, constant with time. Let's say that the time interval would be from 0 to delta t, which would be how long we turn the engine on for. With a little integration magic, we should end up with this equation. This denominator here could be thought of as the mass of the rocket, while the denominator is to final mass. And, well, there we go. There's our equation. Why should I care? This equation captures the essence of rocketry in a simple equation. With a simple equation, you can determine whether your rocket can successfully go to space or not. With a simple equation, you can determine how much payload you can send to space. With just a simple equation, as Tsiolkovsky originally intended when he first derived the equation, we learned that there was hope for humanity to reach the stars.
so uh, yes, I know this is a very simple equation, but it has limitation. Of course, because it is just a 0D, uh, and the velocity, exit velocity, we assume that it is constant. Okay, although you know that you have fire flares at the nozzle, you have turbulence and etc., and those are not constant. And then it doesn't take into consideration any external forces such as skin friction back, or maybe pressure imbalance. Again, another one is the instantaneous propellant injection. The propellant actually it is not constant as well. And they also assume that the rocket is only a point mass. It is not a entire vehicle. Okay, so those are some of the assumptions. But anyhow, good point that you can have. You can see later in a rocket they put more than 10 of the payload of the rocket for fuel for propellant. The remaining 50% is the payload. Okay, where they determine how much payload that we can do. All right. So those are the limitation that I mentioned just now, and of course, like I say, they assume that the exit velocity is constant. We need some numerical calculation where the 3D effect where the longitudinal directional force come into the picture, and then the gravity pull, and also more advanced combustion modules. These are some of the rockets in the modern era. Brothers and sisters, you can see the left side, those are the space agency, okay, for specific country. Malaysia, we do have one which we call as MISA, Malaysian Malaysia Space Agency. And then the middle one, the right one is a rocket engine manufacturer. This is some of you lah. SpaceX, Ariane, Rocketjet. So now we do have Rocket Lab as well in the pipeline. Virgin Galactic, Blue Origin, and etc. Usually Safran build electric propulsion. It is bought by Ariane Group. So rockets launch once every 3 days. This is the statistics. Okay, this is in 2023 launches. Look at the United States, 107, China 63, and then by family. Okay, usually the China rockets denoted by CZ lah. Okay, Falcon 9 frequent lah. Uh, this is 2024. The 2025 in the first 2 quarter they do have the data, but I don't retrieve yet. So China and others, of course, the United States is leading the way due to the SpaceX grant from NASA and etc. For your information, when I visited Ariane, Ariane Group in France, they still have backlog, so they can manage to build at least at most 18 rockets a year. 18 rockets a year. But the demand from the satellite manufacturer and the countries and other countries is much bigger. So that's why this they need what do you call it, a new startup, new company to build other vehicle for other options. And but to your information, in terms of the space worthiness as compared to airworthiness in aviation, space worthiness does not have that many rules yet. It's not as easy as compared to an aircraft. Okay, all right. So these are some of the statistics. You can see that the trends are going to the small satellite lah, the nano satellite, the pico satellites, many on the what do you call it, communication purposes. Okay, communication purposes. The thing is, if you control, you are controlling the wind. Why? Because yes, you see that the speed, the like Starlink, it serves you as a service for communication, but what you know is that it have the data of this information. This is the comparison size of what we have up there. Okay, ISS, you have Black Bear, the size of Mars orbiter, Horizon, Cassini, Star, Hubble, 10 centimeter by 10 centimeter by 10 centimeter lah. And then you have 2U, 3U, 6U. So this is the nano satellite. And these are some of the satellites launched. You can see that we have thousands up there. It is crowded. Okay, but speed it has is huge. So you can see at the momentum equation, mv, although the mass is small, but the velocity is high, it will create a big momentum. And if it is what do you call it, collide, they will what do you call it, create a debris, and this small debris will again collide with other satellite as well. This is what we call as a syndrome Kessler effect. Okay, some space agency, many of space agency, sometimes a company, individual, institute, and etc. So China and United States are leading the way for this, and for Malaysia, yeah, not many, but we do have few lah. All right, these are some of the application for satellite, remote sensing, technology development, commercial. Again, all this we need to have a launch vehicle. So you can imagine one rocket, one launch vehicle, it carries many satellites inside there, maybe 20 and 30 satellites, small satellites. Okay, for the huge mission, for example, James Webb Telescope, of course that one is only one payload. So why don't satellite fall out of the sky? They do have many types of orbit. So using the Topsky equation, so for example, you want to insert your payload at geo, for example. So how much mass that you need to put, mass in terms of propellant mass and also payload lah. Okay. So the nearest orbit, we call this as a LEO. You can read this on your own lah. Medium is medium Earth orbit, orbit twice a day, used for GPS and etc. And then geostationary. Geostationary, it is a satellite that move with the movement of the country. Okay, so when you have a satellite dish at home to watch, maybe to watch TV, so you can see that your dish doesn't move because your country does have geostationary geo satellite. So the satellite move with the country. Okay, Mio, and Geo. Okay, so it depends on the mission itself, the purpose. Okay, I don't want to go into details, but yeah, at least for you to know. Altitude, you have eccentricity. Eccentricity, how far off it is from the circular or circle orbit. All right. So if you have high eccentricity, means it looks more elliptic. Okay, orbital inclination, it is the angle between the equator. This is where you place lah. And again, brothers and sisters, in order for any institution, any country, any university, any company, if you want to book a slot to place your satellite, you need to apply it to UNOSA. They have a slot for you. Again, if that slot is empty, then you will be granted. If not, you have to find other slot. So from that slot, from that height, from that inclination, from that eccentricity, so they have their own data to check whether it is available or not. Then if you get the permission, of course, you need to launch it. When you need to launch it, the launch vehicle provider, what they need to do is to get your certification of several tests. All right. Another statistics, okay, like I said, in 2020, look at the number. This one is during COVID. Launch vehicle 114 at 21 sites. So it is every 3 days one satellite, one rocket is being launched. So this is roughly the statistic lah. Okay, at the moment, what do you call it, since 1960 until now, 73,000 have been attempted, or 1942, sorry, until 2022, 70,000 what do you call it, launch vehicle tests, launches, and etc. So, however, this is the what we are still worrying. In terms of the percentage of failure and success rate, the success rate is 92%. Is quite low as compared to the aircraft. Aviation sector 98% and 99% lah. But rockets still quite low. Currently, it start to increase 93 to 94% of the success launch. And look at the launch area. Okay, you can see that many launch sites are at the equator. Why equator? Because at the equator, the Earth move faster. Okay, the Earth move faster at the equator. So you will have a more inertia for your rockets to achieve the target delta V. Every mission you have every mission or every altitude you have your own delta V. Okay, delta V. Okay, and then also you do have escape velocity. What is escape velocity? Escape velocity, it is a velocity where the gravity pull is not influencing the object. So that's why it keeps on orbiting. I will tell you about this later. So in space economy, you have upstream, downstream, and space derived. What Western country have? They have the full spectrum. They have the upstream space sector. That is why I really encourage our neighboring country, ASEAN country, go into the upstream space sector, because this is where they build the technology, rather than, because if you know upstream technology, you know the core of the technology, for example, the thruster, the chamber, the nozzle, and etc. So you can do many things. All right. The downstream, it is what you call it on the ground, where the operation in space infrastructure and space derived activities in under sector. Currently, I'm talking about Malaysia. Malaysia still in the space derived activity. Yeah, some a little bit on downstream. But if we know the core, the gist of the technology, which is at the upstream technology, yes, I know that you have different view. For example, why on earth? Maybe you question this thing. Why on earth United States and the European build space James Webb Space Telescope just to monitor, just to view, just to investigate the birth of the star, the birth of the galaxy, the first light, the photon lights, or to study the first 300,000 years after the Big Bang. Why you want to study, spend in so much money, billions, I'm talking about billions of dollars, for such of these technologies, which is James Webb Telescope. This is what we see. But what we don't see is that they are actually build a space-derived technology. For example, in the Space Webb Telescope, what they have is they have 100 micro shutter in a very small region. Later on, it will be used in our smartphone. They have a technology to spray gold into the mirror, to the mirror, very fine spray. So this spray, this nozzle, spray nozzle, can be used later in the engine, in the internal combustion engine lah, and other things lah. Okay, you can see that our, for example, milk baby powder, milk powder for babies. It is a space technology where they build this, NASA invent this for astronaut in ISS. Formula milk baby. And then sports shoe is a space derived technology as well. Okay, so the thing is, if we in ASEAN, especially this developing country, not embarking on this upstream space sector, we are actually going behind. Okay, so this is industry economy globally. Like I say, in 2040, they are targeting $30 per kilogram by 2040. This is the scenario. So everyone goes to space. We don't currently have any space law for the universe, for our Earth, saying that if any country has a technology that can do space mining at asteroid, the scientists found one asteroid nearby full of diamond worth more than 100 trillions of dollar. So we don't have yet any law that prevent any country who has this technology mine the diamond or mine the diamond and bring back to the country. So at on in the outer space, it is for everyone. So that's why people are going rushing through the space, not just demonstrating technology, not just creating technology, because in space they have abundant of minerals and also alternative energy. For example, another example is the moon. Okay, the closer one is not the closest one is the moon. Look at the moon. At the moon, they found that they have helium 3. Helium 3 is an alternative energy sources, a clean one for nuclear reaction. So they don't have any law that, what they call it, prohibit any country to mine this. Right? So that is space economy. This is the reality. China is going bigger. Of course, it's 2023 lah. And you can see that the value, their predicted value, 1 trillion in space technology in 2030. This is by the Bank of America. This is the value of the space economy, not just upstream, but also downstream as well. Okay. All right. So that is first part. Okay, let's look at the rocket flight performance. Everyone knew this. When you look at this video, let me play this video. You have watched how rockets travel. So it starts from refilling the propellant and then ignition and then liftoff. Okay, that is the normal procedure. And then ascending until it reach Mach Q, the maximum pressure. And then if the tank finish, so it release back. So this is what we call as a multi-staging. So one by one, this is the third staging where it cruise to the mission. That is not a wing, that is a solar panel for the spacecraft to travel. And then again, it is not vertically, it moves, it turns, gravity turning, and then go to the mission lah. In this case, the mission is go to the other planet. So again, when it enters any heavenly bodies, it has to circle, okay, orbiting, all right, orbiting the planet or the heavenly bodies, and then when it lands, they have to slow down a little bit. Okay, slow down a little bit. The drag is tremendous high. You are talking at this speed of hypersonic, and you can see that in a hypersonic flow, the shape of it is bluntly shaped. Okay, bluntly shaped to create drag and to deal with hypersonic flow, the bow shot. This is how it lands. To slow down using parachute. So you can see that it is fiery when entering, not when ascending, because the spacecraft moving from less dense to higher dense. As compared to ascending, we are moving from dense atmosphere to lower dense. Okay, so the space flight, space launch, orbit, and re-entry. So into the space, you know that we have different multi-stage, and fighting the Earth gravity is really hard. So you need to, of course, the speed depends on altitude. So for sea level, it's around 7 kilometer per second. that you must achieve this, and the rocket fuel is of course very expensive. They are using for kerosene RP1 for kerosene lah. If they use methane, okay, it is in liquid form. And then hydrogen, a cryogenic fuel, it is hydrogen in liquid. You can imagine hydrogen is a gas. You need to compress and you need to have a low temperature, so it can be a liquid. All right. And also liquid oxygen. Okay, that's why it is very expensive. And rocket engine burns at very high temperature. You will see later how much is the temperature of the nozzle at the nozzle. So thrust going up, going down. This is again repetition. So this is how you have. Okay, so you have two tanks, fuel and oxidizer, and a separate pump. We have different types of pump. Some of the pump pumping the tank, some of the configuration pumping the feed line before it enters the thrust chamber. So this is the thrust chamber where the oxidizer and fuel is mixed. When it is mixed, ignite, it will combust. So from chemical energy to heat energy, and then the gas expand at the converging diverging section, and then you have a kinetic energy. So the Dutch rocket, you can see that most of it are tanks, propellant. This is the different. This is the different in terms of mass percentage of propellant. Ship 3%, payload you can carry 30 to 60%. But look at rocket engine. Propellant is 85% and the payload is only 2%. This is the temperature of a rocket engine. You can see that it can reach up to 3,500 Kelvin. Okay, so you can see that you have many. This is not due to heat. This what you call it, the kind of smoke. This is for cooling. Okay, for cooling, so that the wall of this nozzle does not melt. So you have this fuel, oxidizer inlet, you have turbo pump. Okay, this is one schematic drawing. We do have two types, like I mentioned before, and then everything being injected inside the thrust chamber and expelled out. And those are for launching and then orbiting, flight in space. Okay, like I said just now, when you go up into the mountain, when you go up to the mountain, if you throw 3 kilometers per second, you throw a ball, 3 kilometers per second, it will start to drop. You throw faster, it go more further. 5 kilometers more further, 6.5 kilometers more further, 7 kilometers more further. But when you achieve 7.3 kilometers per second, the ball start to rotate. This is what we call an escaping velocity. But this escaping velocity reduces as the altitude increases. So that is why a rocket needs to fly higher so that the escaping velocity is not that large. Okay. Now the ball doesn't fall down, it starts orbiting lah. Okay. So this is why the space, the satellite can stay in the orbit, because it is there. It achieved already the escaping velocity. Our ISS also moving, everything is moving in outer space. But my question is, although everything's moving, okay, but does outer space has gravity? Anybody can answer this, to show you that you are still there and awake. My question is, brothers and sisters, in outer space, in ISS, does gravity exist? Hmm. Our astronaut floating inside the ISS, so it floats. Does it don't have any gravity? Oh, you're all muted. Never mind. Okay, the simple answer is gravity exists. Gravity exists. Even though the moon is much further than the ISS, even though the sun is much further than ISS, the gravitational pull still exists. But if the gravity pull still exists, that's why you have tide, the wave, and etc. But why does the astronauts floating? The astronaut float not because they don't have gravity. It is because that the astronaut is fall freely. Okay, free fall, free fall. Free fall, you can imagine like this. You are in the lift, you are in the lift, and then you have a building. This building maybe 100 stories. Okay, so you are inside the lift, so you go to 100, the 100th floor. Okay, and then you are in the lift and somebody cut the cables. So when the what happened to the lift, the elevator, what happened, it will go down. Okay, it will go down. But you inside this elevator, inside this lift, you also go down, but you tend to float. Okay, this is what we call as a free fall lah. So these are the condition of the astronauts at outer space. So, like I say, it move in orbit, okay, and to fly and to enter also in orbit. We use sometimes a convergent and divergent nozzle. We call this as a D level lah. Okay, D level nozzle. This bottom left graph. This shows the thrust versus ISP, specific impulse. Okay, you can see that space shuttle has higher thrust but low ISP. ISP you can imagine like specific fuel consumption. Okay, specific fuel consumption means higher ISP is better lah, but not necessarily high ISP you will get high thrust. Okay, so usually electric propulsion has high ISP but less thrust. Okay, okay, how do you know that the nozzle work fine? You look at you monitor, you observe the flame. Okay, what we want, we are talking about the bottom right, bottom right figure. What we want, ideally, it is fully expanded nozzle. Means what? This is what we call as the design condition, ideal condition. So the right one, this is the flame, the yellow color. This is a nozzle which has the what do you call it? Divergent angle, length of the nozzle just enough for the gas to be expanded. What we want in the nozzle is we want to expand the gas, fully expand. So the right angle and also the right length. So the flame looks something like this. This is what we want. This is ideally. But usually what happen is the nozzle underexpanded or overexpanded. Underexpanded means that the nozzle is not enough to expand the gas inside the nozzle. So the flame will expand outside the nozzle. So this is what we call under-expanded nozzle. Nozzle is not enough. What about overexpanded nozzle? Overexpanded nozzle is a nozzle where the nozzle is too big or too long for the gas. So the gas is already expand inside the nozzle. So that's why the fire converge, the flame converge. All right. So you can see that many of the rocket being launched is somewhere under expanded and over expanded lah. Okay, why I am saying this? Because this phenomena often dependent to the ambient condition. Rocket move from lower altitude to higher altitude. What happened at higher altitude? The pressure is less. So when the pressure is less, the flames start to expand outside, so under expanded. So that's why you can see the fiery from the SpaceX, it is under expanded. But can we avoid this? Yes, we can. If we can find a nozzle like a rubbery type of nozzle where it can close and open up the fire based on the ambient condition. But unfortunately, we don't have this yet at the moment. Okay, so so this is not desired lah under expanded novel. So why is not desired? Because you lose the energy that can be converted into kinetic energy. For example, under expanded, gas is not fully expand inside the nozzle, so you will lose some of this heat energy outside to the surrounding. What about under overexpanded nozzle? Overexpanded nozzles means that you have separation inside the nozzle, so you will lose this kinetic energy as well. Okay, from heat energy. All right. So these are a little bit of the trajectory. Okay, where it flies. Of course, you cannot fly. This is just to save fuel lah, economically. Yeah. Okay, we are trying to find the time where the Mars and the Earth close together, and then this is the gravity slingshot. Gravity slingshot. If we want to travel to deep space. Okay, so like this. So it moved from one planet to other planet using this gravitational pull, so that the mission, so that the spacecraft can travel to the next planet. Safe fuel lah. So again, the space is not big inside the launch vehicle, and the geometry of the satellite is not symmetry. So you have to play around with many types of what they call it degrees. So these are some of a little bit of the payload, which and then re-entry. You can see that re-entry, the shape, the aerodynamic shape is more blunt. Why? Because we are dealing with hypersonic flow. And then in a hypersonic flow, you deal with bow shockwave. Okay, bow shockwave is different. Supersonic aircraft, jet fighter, and etc., you can see that the shape of an aircraft, it is sharp because you are dealing with what do you call it, conical shockwave, oblique shockwave. But hypersonic, you are dealing with bow shockwave. So that's why it is different. So imagine you want to fly back to Earth in hypersonic speed. You are talking about 5 Mach number and above. 5 Mach number is 5 times the speed of sound. How much is 1 Mach number? At a sea level and what they call it, room temperature, is around 340 meter per second. So you can imagine if you move at 5 Mach number, so 340 multiplied by 5, okay, 1000 something per second. Okay, this is how fast it is. So how can the astronaut inside the vehicle survive in this journey? Of course, you have a protecting thermal insulator. So these are the concept previously they have studied. This is the top left is the oblique shock wave. When you have a blunt nose in the current technology, in capsules, you have a bow shock wave. This bow shock wave is important. Why? Because it protects the surface. Okay, it disseminate the heat transfer from touching the surface of the capsule. Okay, 1000 of degrees Celsius. So how can we shield against such as heat? So they are using a special tile lah. So imagine at 2200 degrees coming up from the oven, the person there can straight away touch the tiles. This is the technology that we have currently. So how to control the surface? It has no wing. It's just using what they call it as a jump. Okay, and when it enters, speed when it is entered, it has another injection and then go up first. Okay, to reduce the speed and then coming back again. Okay, this is a little bit of jump there. Okay, all right, so this is the picture. Now selection, like I said, chemical rockets, we do have liquid, we have solid and hybrid. Liquid propellants, again you have two types. One, the tanks look like this, the second one looks like this. So the first one, what happened is the turbo pump to pressurize the oxidizer, to pressurize the fuel, it is pressuring at the feed system, feed line, before it enters the thrust chamber. Another configuration is that you have an inert gas where it compress the fuel tank and the compressing the oxidizer first before it inject inside the thrust chamber. Those are the two types of mechanism in liquid propellant. You can see that in liquid propellant, those two configurations need two different separate feed line system. And you can imagine both fuel and oxidizer has to meet at a certain mass ratio so that you can burn it. You in rocket combustion, in combustion of rocket, they don't mix at stoichiometric condition. Stoichiometric is ratio of 1 to 1 lah. Okay, 1 to 1. If you have a chemical formula, okay, a number of moles, just enough number of moles of oxidizer and fuel, that is stoichiometric condition. Okay, but in rockets, they combust oxidizer and fuel at a rich condition. Rich condition means that the number of moles of fuel is greater than the stoichiometric one. Okay, so this is usually in rockets. So at stoichiometric, yes, at stoichiometric condition, the flame temperature is at the peak. But again, we don't want this. We want to burn at rich condition for many reasons lah. Okay, I know that it's not economically feasible, but the flame temperature started to reduce. Solid propellant, solid propellant, both fuel and oxidizer in solid states, and it is binded together. You have plasticizer, you have binders in place inside the solid and oxidizer. Hybrid propellant, the liquid, the fuel and oxidizer in different physical state lah. Okay, you have liquid oxidizer, you have solid fuel, and it burns inside the combustion chamber. So these are the several characteristic of chemical rocket, how we want to compare chemical rocket propulsion system. So the feature on the left, and then the chemical rocket, turbojet, ramjet. Turbojet engine is the jet fighter one. It's air breathing engine. Okay, jet fighter. Ramjet engine is an engine with no turbo machinery, no fan, no compressor, no turbine. Okay, it's, for example, Concorde. Okay, you can Google Concorde. They don't have any moving parts. Okay, that is a ramjet engine. We do have scramjet engine. Okay, where is the difference between ramjet and scramjet engine? Scramjet engine burns at supersonic flow. A ramjet engine burns at subsonic flow. All right. If you compare in terms of thrust to weight ratio, this is an important parameter. Rockets engine 75 times. Okay, 75 times than the weight as compared to the weight. In terms of specific impulse, specific fuel consumption, it's quite less. It is not safe. 8 to 14. Okay, it uses many fuel. Okay, turbo engine is much saving. Ramjet engine not economical as well. In terms of specific thrust, this is how high it is. So if the specific fuel consumption is not good, so you can expect that the specific impulse will be reduced lah. But in terms of thrust change with altitude, you can have slight increase, but turbojet engine decrease, ramjet engine decrease, because those two are air breathing engine. You don't have enough oxidizer enough air into the engine. So that is why at high altitude, the thrust will start to reduce. Flight speed nearly constant, increase with speed. Thrust versus air temperature constant, flight speed unrelated, and then because you don't have limited thrust. Uh, the right one, the right table, chemical, this is the comparison between chemical rocket, which is solid liquid or hybrid or liquid, and resistojet. Resistojet is an electric propulsion. Hall effect, arc and heating, arc heating, Hall effect, iron, those are electric propulsion. And then you have a solar heating. So you can see chemical rockets does not perform that well in terms of specific impulse. This is the range of maximum temperature. Look at the arc heating, 20,000. Thrust to weight ratio, you can see chemicals much better. All the electric rocket are not. In terms of duration, you can see that in a YouTube video where the space flight we have for SpaceX Blue Origin, it does not last for long, in few minutes or in seconds only. But electric propulsion, days and weeks, sometimes years. Okay, it can sustain. Power, this is the power needed for a chemical rocket, specific power. Liquid propellant, liquid working fluid is either liquid, solid propellant. All these are proven, but solar heating is still in development. Electric propulsion, they use, of course, xenon, sometimes argon, depends on the mission itself. Sometimes also is krypton as well. All right. So in terms of velocity, electric propulsion is much higher. All right. But in terms of acceleration, gravity, thrust, or thrust to weight ratio, it is much lesser. This is the configuration of a solid motor. You can see that it is maybe it is cartridge load grain, or is it a case bonded grain? Cartridge you can slot in. Case bonded, the case itself, it is entitled with the body. All right. And the burning for solid motor, it can be regressive burning, it can be neutral burning. This is thrust, and it also can be progressive burning. This burning depends on the geometry. So you can play around with the geometry of a solid fuel, whether you want to be a star, wagon wheel, multi-perforator, dot bone, or dendrine. So it depends on the mission as well. So as you know that the solid propellant in the later chapter, you will see that it depends mostly in the geometry as well as the pressure inside the solid fuel. All right, example of solid propellant. This is what shared by the Sutton book. Okay, you have binder, plasticizers, solid oxidizer of fuel, and propellant application. So binder using NS. Sometimes we use HTPB. HTPB is hydroxyl terminated polybutadiene. It's a good one. Plasticizer, I normally use IPDI. Okay, solid or fuel, solid oxidizer or fuel, aluminium. AP is aluminum perchlorate. KP, HMX. Okay, some for booster application. For booster, the designation is how they cast. Okay, how they cast. Is it a double base, or maybe is it CMDB, composite modified double base, or is it EMCDB? It is elastomer modified cast double base, or it is a polybutadiene. Okay, polybutadiene. HTPB is a polybutadiene, hydroxyl terminated polybutadiene. All right, this is how designation for solid propellant. To compare with the oxidizer, okay, you have fuel, next you have oxidizer. So oxidizer, you can have AP, ammonium perchlorate, potassium perchlorate, sodium perchlorate, or ammonium nitrate. So again, it depends on your mission. For ammonium perchlorate, I know that it had, okay, what is lower N? Lower N is a superscript of the performance. You will see later. This is the lower N. It is a low cost, readily available, and high performance. PP, which is potassium perchlorate, low burn rate, medium performance. High performance is sodium perchlorate. Ammonium nitrate is a medium performance and low cost. Usually, what for my experiment flight test, I'm using AP, yeah, ammonium perchlorate. Liquid propellants, these are some of the examples. Okay, uh, for for oxidizer. Okay, the left one is for oxidizer. The right one is fuel. Okay, so oxidizer, liquid oxide, nitrous oxide, nitrogen dioxide, nitric acid, and sorry, my mistake. These are all the propellant, not not oxidizer and fuel, because RP is fuel lah. Liquid oxygen, nitrous oxide, nitrogen tetroxide, liquid hydrogen, liquid methane, those are all fuel, propellant. Or we can also use water, but it depends in the company. For example, SpaceX, they are very well aware or know the technology for methane, so that's why they use methane. Methane and oxygen. Sometimes they use liquid hydrogen and liquid oxygen. ESA, some of the company as well use RP. RP is rocket propellant. Hydrocarbon, it is a kerosene. Okay, using RP and liquid oxygen. Rarely now using hydrazine and monohydrazine because and nitric acid, sometimes because of the toxicity. So those are liquid. Now electric propulsion, like I say, divided into three parts: electrothermal, electrostatic or ion, and the last one is electromagnetic or magnetoplasma. The same working principle. They want to heat the propellant so that it has enough heat energy that can be converted into kinetic energy. So the first one, electrothermal, using a thermal or using electricity. Okay, electricity to heat up the propellant. Okay, electrically, and expel out. But the thrust is around 0.01 Newton to 0.5 Newton. This is electrothermal. Electrostatic, using ion. The working fluid or propellant is ion, stripping from the electrons and accelerated out 2,000 to 60,000 meters per second. Again, brothers and sisters, although the velocity is high, the exit velocity is high there, but the m dot is not big. You are talking about ion. Ion, how much is the weight? It's very, very little. Okay, and then you have a magnetoplasma, using a magnet inject the plasma. Plasma is another form of physics. You have liquid, you have solid, liquid, gas, you have plasma. Also at high speed, but again, you are talking about neutral particles. You are talking about electrons, not that heavy particles injected out. So these are the comparison. Okay, those electric propulsion, it is again for cruising. Okay, cruising. So this is the arc engine, MDP arc engine, whole thruster, ion engine, and Teflon thruster. Okay, this is how the technology. Uh, I have seen this in my life in front of me when I visited Safran in Vernon. Safran Group. So the size of this electric propulsion is not that big. Okay, it can be the size of your notepad, it can be size of your iPad, and maybe it can be a size of your desktop itself. Okay, it's not that big. It depends on the power that you want. Okay, the thrust that you want, then the power that you need to have lah. Okay. Okay, so again, in a rocket, you have different types of system. Propulsion system, GNC is ground network control, C and DH is control and data handling. Okay, so those are the division. Okay, in propulsion, of course, you have single, serial, or hybrid. Single, serial, parallel, or hybrid, it is the how you want to make it in the for the multi-staging. And then the requirement, Mechanism, structure, difference between monocoque and semi-monocoque. Semi-monocoque is a structure like an aircraft. It's not a solid structure. And then whether you have internal or external skeletal, whether you have single or multiple tanks, again, like SpaceX, when they have many nozzles, many engine, Raptor engines in their rockets, the thrust, one thrust chamber, one nozzle. It can be like that. Or it can be one thrust chamber, three nozzles. Okay, that's why I'm saying that. Is it a multiple tanks or single tanks? Okay. Engine, whether it is solid, liquid, and hybrid, these are the some of the propellants. Whether the pump is a pressure-fed turbo pump or piston pump. And then this is the orientation, whether you want it to have a series or tandem, partial staging, parallel staging, like a normal one that we have, for example in Ariane 5, or piggyback. Piggyback is like a space shuttle lah. Okay, these are some of the maturity that has been used in the current technology. For launch vehicle, usually we use liquid and solid. We don't use electric propulsion system. Okay, this is for launch vehicle. For orbit maintenance, some are using liquid, maybe they are using gas as well, and of course they do have many in electric propulsion. Docking of two spacecraft. Docking, it is when, for example, a capsule, an astronaut in a capsule want to, what they call it, have a mission to ISS. Docking, it is where the capsule and the ISS meets. Okay, re-entry and landing using a liquid and solid, rarely using electric propulsion because it needs high thrust. Deorbit, okay, deorbit means what? Means after every satellite, it has a lifetime. So for example, we design a satellite for 2 years. So by the time of 2 years, we need to end the life of the satellite. So we need to deorbit, go up from the orbit, maybe to what they call terminate the satellite. This is deorbit. Deep space, of course, we have electric propulsion, tactical missile. Okay, this the last four part is more on military. Okay, missile, strategic missile, defense, so those are usually solid lah. Much cheaper and not that complex. But again, if you are using solid propellant, solid motor, usually, yeah, brothers and sisters, uh, liquid rocket, we call this as a rocket engine. Solid rocket, we say that it is a solid motor. Okay, so we do have many advantage and disadvantage, of course. Solid rocket, usually you cannot control. Once it is ignited, it will finish until the end lah. So that's why we use this in a military target missile system. Liquid rocket, yes, we can control. We can control the feeding line, the feeding system for oxidizer and liquid. Hybrid rocket also we can control. Compare liquid and hybrid. Hybrid is much simpler because we only have one feed line system. Nuclear, okay, this is nuclear rockets. I won't go into deep details because it is just what they call it. They wanted to go to this direction, but they have quite a problem because of the radioactive issue. But the principle is the same. Nuclear thermal, they are using a nuclear fusion or fission to heat up the propellant and expel. That's why they call this as a nuclear thermal rockets, using nuclear reaction to heat up the propellant. Okay. Okay, so using nuclear reactor, propellant, thermal fission. So of course, advantage, high specific impulse, thrust capability, can extend reduce time level. Challenges, radiation, safety, thermal management, and also engineering complexity. When I When I visited the conference in the United States, AIEE is American Institute of Aeronautics and Astronautics in Washington D.C. Last 2 years. Now the direction of NASA for interplanetary missions, they want to start back the nuclear thermal engine rockets, because it can travel much faster and much minimum fuel consumption. Okay, they are working on this. Solar cell, this is the photons, photon momentum that I show you just now. Again, this is not, it is feasible physically, is physics and physically and mathematics, but engineering currently they are experimenting it. Advantage solar panel, as you know, no propeller required, unlimited resource source, scalability, and simplicity. This is the Vasimer, another emerging technology using magnetoplasma. Again, this one is still electric propulsion. All right. So, what is the propulsion? Propulsion is the act of changing motion of a body with respect to inertial reference frame. So, the propeller means to drive away. So rocket propulsion is a class of jet propulsion that produce thrust by injecting matter. This is what I mentioned in the early of the class. You want to eject the propellant out, which has been stored in the tank. So it is can be inductor propulsion or duct propulsion is a class of propulsion includes a turbojet ramjet. But now we are talking about rockets, which is not everything. Okay, in terms of classification, okay, concept, turbojet, this is already matured. Turbo ramjet, TFD, okay, or ramjet, TFD. Ducted rocket, TFD. Electric rocket, DP, okay, means that it is already developed. Nuclear rocket, TFD, okay. Technical feasibility then also has been demonstrated. Photons rocket, this is a big light bulb, still TFND, which we call as technically feasible, but has not yet demonstrated. So these are some of the concept where it is classified of the different energy sources. Chemical, we are talking about liquid, solid, and hybrid lah. Nuclear, for hybrids, what are the example? Hybrid rockets used by Virgin Galactic, Spaceship 2. Okay, for astrotourism, if you can still recall, we have 3 billionaires working on astrotourism. We have SpaceX, we have Blue Origin under the Jeff Bezos, Shepherd, and then the last one is Virgin Galactic under Richard Branson. So both two, SpaceX and Blue Origin, they are using liquid and solid rocket lah. Okay, while Richard Branson, Virgin Galactic, use hybrid rocket. So it takes off from an aircraft and then turn on the rocket booster using hybrid rocket, using rubber, and then fly off to the Kármán line lah. Okay, you can view this in the YouTube. How does the VSS, the Spaceship 2, flies, take off? I think few years back, 1 or 2 years back. Okay, this is a ducted jet propulsion. Again, this is everything. Okay, this is the schematic. This is a turbojet. You have a turbo machinery part, and then ramjet, you don't have a turbo machinery part. So you have an airflow and then mix inside the combustion chamber. Okay, this one I have showed you just now. Okay, so the rocket propulsion system can be classified according to the energy source type in previous slide. Basic function, whether you are talking at the booster stage, it is from the ground level, sea level. Sustainer, it is on the upper stage, or maybe you want to use it for the altitude control or orbit station keeping. Okay, orbit station keeping, what is it? Orbit station keeping, for example, ISS. They want to maintain the altitude. So you know that And outer space, maybe you will lose some, you will lose your velocity. What happens if you lose the velocity? Due to the perturbation. Perturbation can become from many things: the oblateness of the Earth, the space weather, and etc. If you lose the speed in outer space, the gravity will pull you down. Okay, gravity will pull down. So that's why orbit station keeping, to keep the velocity at that particular altitude and at that particular orbit lah. The third one, to classify a type of vehicle they propel, whether in an aircraft, missile, or assisted takeoff space vehicle, or size, type of propellant, type construction, and etc. This is how usually they classify a rocket propulsion. So what we want from the internal energy, which is the chemical energy, converted into exhaust energy lah. Okay. Chemical, okay, this is the range. This is just again a repetition, but this is more on my class. The previous one slide that you saw just now, those are the slides where I go for outreach to the community, to the public, teaching them rocket propulsions. So these are the units. I know it is wordy because this is the undergraduate slides. Typically from 2000 to 4000 degrees Celsius, and the speed VE, velocity exits, around 1800 to 4300 meter per second. Now I'm talking about chemical rockets. We're talking about liquid and solid propulsion rockets. All right, the liquid propellant engine use a stored liquid that are fed by propellant, means that the liquid fuel by two lah. One oxidizer, maybe oxygen, and then another one is maybe hydrogen or methane lah. Monopropellant, this is where the liquid, liquid propellant, the oxidizer and fuel in a liquid state at one single tank. This is the big picture. Okay, the size, the schematic of the drawings of this pipeline system. You can have a liquid propellant rocket engine with gas pressured feed system, or maybe you are pressuring at using a turbo pump at the feed line. Solid and liquid, another one. Okay, you can also have a combination, like I mentioned before, using air breathing engine, ramjet, and then turn on the solid motor. This is usually for missile, okay, missile, from like a Tomahawk, okay. Nuclear rocket, again, still public concern about the accidents, the radioactive accident which can cause. Electric rocket is why we call this is high performance? Because the ISP is high. The fuel consumption is very low. So this, but the amount of thrust that it produces is quite low. It is too low that it cannot use to launch an atmospheric flights. Okay, electric propulsion utilize energy sources, nuclear and etc. contained and being utilized. The thrust usually is very low. You are talking about less than one Newton. This is the slides that what do you call it? I have compressed this in the previous slide. This is the schematic diagram. Okay, arc thruster, ion thruster, and also magnetoplasma. This is the schematic that I won't go deeper into this because this is more into electronics part, more on physics part, where they rip off the electrons from their ground state condition. Okay. Other rocket propulsion concept, solar thermal, like this one. Okay, the thing is, okay, it have a parabolic reflector. What happen is they have a radiation from the sun. This sun will collide with the reflector, and it is focused on one heat receiver. This heat, what will happen? It will heat up the gas, the hydrogen gas inside this receiver, and then expel out. Okay, so the means is heat from the sun. Nuclear, it is hit the propellant, it is hitting the propellant using fusion. Electric propulsion heat the propellant using electricity. So that is the concept. Right? So that is a solar thermal. Space launch vehicle, okay, 95% launch record. This one, the statistic until 2016. 2016, but in the 2023, in the previous slide, it has reduces. Why it is reduces? Because now we are moving to privatization. So startups, local company start to build their own. Before this, we see that all the space mission coming from the government. All right. So space launch vehicles or base water can be broadly classified as expandable, type of propellant, number stage, etc. It uses maybe it can use from 2 to 5 stages. This is multi-staging. Uh, so this is the comparison between Delta 4 and Atlas 5. The configuration, it can be a piggyback, it can be a parallel, side by side. This one, the right version of Ariane, yeah, this is Ariane. Uh, okay, the new version is Ariane 6. Okay, Ariane 6, the booster, the stripe at the side can be changed, 4 booster or maybe 2 booster for different mission. This is the new technology that they impose lah. Space shuttle, it is nice to see, nice to look, but it is very costly. Okay, before this, they use what they call it, like an aircraft for the re-entry. But now we have a TVC. TVC is thrust vector control, where the gimbal of the nozzle can land back again during the re-entry. So spacecraft can be categorized as Earth satellite, lunar, interplanetary. There are over than 20,000 satellites out there. Categories depends on the mission, whether it is communication, weather, navigation, scientific exploration, deep space, observation, and reconnaissance. So rocket propulsion, we do have both primary propulsion and secondary propulsion. Primary usually using a big, what do you call it, big rocket engine lah for thrust. Secondary propulsion usually at the side of the rocket, okay, for the adjusting, for altitude control, for spin, for momentum wheel, gyro, stage separation, and etc. Those are secondary propulsion. Primary propulsion, it is from the main engine itself. Okay, so you have, depends on how many thruster that you want. Sometimes they have many. Raptor engine, they have 32 thruster. The thing is, put it this way lah. If you have many thruster, many nozzles, what you can do is that the nozzle can be shorter. But if you have 1 or 2 thruster, or maybe 3 thruster, your nozzle should be long. Okay, there are pros and cons. If you have many thrusters, you have complexity, but you can save the size of the nozzle, the length of the nozzle. If you have less nozzles, the complexity is low, but the length of nozzle is much higher, and it carries more weight lah. All right, so this is a military. Okay, this one I've mentioned this one in the previous slides. What they have, it can be a military satellite, weapons, surface to missile, and and battlefield support, anti-tank, and lunar landing. So I think that is all for lecture number 1 for today. So it's already 5:50. Brothers and sisters, are you still alive? Are you still alive? Do you want to ask any question? Okay. You muted.
Thank you very much for the first lectures. Very informative, a lot of information. Uh, we can see that you are really passionate about rocket propulsion system. So you're not tired at all. You've been nearly 2 hours lecturing, right? We can take a break in between next time, next lectures. Yeah. Thank you very much. So
Welcome.
yeah. If you have the quiz or the problem for the first lectures, please share with me on the share Google Drive. Can you hear me?
I cannot hear you clearly, Dr. Hugh.
I will. I will.
Ah,
Can you hear me now?
yes, now better.
Okay. Yeah, yeah. Um, so please, next time you can take a break in between after 1 hour of lectures. I'm afraid that it's a very tiring mission for you if you lecture
Uh,
for two
I'm
hours
I'm
non-stop.
I'm okay if the children if the students are okay. I'm okay.
Okay. So for the first lectures, if you have quiz or problem, please share with me so that I can encourage students to explore more and review the lectures.
Okay, sure.
Thank you very much.
I will share. Okay,
Yeah.
thank you, Dr. Hugh. Thank you,
So
student.
as agreed, I will give the lectures on the nozzle theory the next week. So we will see you again in the following week.
Okay, sure, Dr. Hugh.
Thanks a lot.
Okay, thank you. Bye, student. Bye. Can we take photo?
Ah,
Can we take photo? Okay,
take
one.
a photo. You like to take a photo?
Okay, one, two, three. Okay, nice. Thank you. Thank you, everyone. Bye.